This video will examine the mechanism of formation of dinucleotides. I plan to show you the way the two nucleotides react to make a phosphodiester bond. I want you to keep in mind throughout this process that this particular process is reversible and it can go in both directions. So I will show you how two nucleotides can form an ester bond and put two nucleotides together. But I also want you to keep in mind that the reverse is possible. The newly added nucleotide can be removed through the opposite process of what I will be showing you. So you can see here that the two nucleotides, one of them is deoxy TTP, which means the deoxythymine triphosphate, and the lower one is deoxyadenosine triphosphate. This is the second carbon of the ribose, okay, right here. I'm going to color it red so you can see it better. And this is the third carbon, okay? So this is the second deoxy carbon. This third one, this is the 3' alcohol group. So I want you to pay attention to this one. And this is the 5' carbon right here, 5', 4', 3, 2, 1. So I want you to pay attention to the 5' carbon, which will react with the upper triphosphate right up here, okay? And you have three phosphates here. So this alcohol group right here, it's going to form an ester bond with the phosphorus atom right here. I'm going to label them alpha, beta, and gamma. Okay, and I'll label these alpha, beta, and gamma for simplicity reasons. As you can notice, right here, everything I have added the hydroxyl groups to each one of these, and normally at a pH of 7 you have about 1.4 to 2 negative charges, but I will call them hydroxyl for simplicity reasons, and I did the same thing right here. Okay, so I want you to pay attention that you already have right here an ester bond between this alpha phosphorus atom and the C5 of the ribose sugar below. So this is deoxyadenosine triphosphate already has an ester bond. So you have an ester bond between the deoxyribose and the phosphoric acid right here. So we will now have an ester formation between an alcohol, I'm going to circle it for you right here, and an acid derivative below, right here. So in the end, we will form a phosphodiester bond, a bond right here, okay, and the pre-existing bond already is there, so we will have a phosphodiester bond between the upper and the lower nucleotides, the TTP and DATP. The upper alcohol, so I want to show you this intermediate step, okay. You have the upper alcohol, I'm circling it right here, will attack the phosphorus atom right here, okay, right there. So a pair of electrons are going to leave this oxygen and they will move to this oxygen. So you will end up, I'm going to draw it with a green color so you can see it better. This positive charge will follow up here and you will end up with a negative charge right there. there used to be a double bond right here between the phosphorus atom and this oxygen, but now it became a single bond. So the two electrons have moved from up here, okay, and they have opened up those electrons. And now you have the negative charge, the positive charge next to each other, and the negatively charged oxygen right here will eliminate. So what we plan to do, we need to eliminate this circled in green. This is called a pyrophosphate on the right instead of water, and we are going to form a new ester, okay? So the nucleophoric attack on the phosphorus group intermediate is seen right here, okay? So you can see the nucleophoric attack, the new bond. I'm going to make it green right here between the upper and the lower nucleotide. And what happens, I'm going to make it all a different color. I will select blue. You can see that the phosphorus atom now has one bond with the oxygen, one with this other oxygen, one with the hydroxyl group, the old bond right here, ester with a 5' carbon, and a newly formed bond with the oxygen above. So there are 5 single bonds, okay? 5 simple bonded groups onto the phosphate. What we do want to do, we want to eliminate the pyrophosphate right here. I'll call it PPI, okay? And when we eliminate the PPI, we will take also the proton. I'm going to circle it in blue. From up here, we are going to take this proton with it, okay? So the lost double bond right here, I'm going to draw it right here. The lost double bond will reform. Where did the proton go? The proton is not here anymore. It has moved right here. And this is the pyrophosphate leaving. Phosphodiester bond up right here. I'm going to make it blue now. And there is also an old phosphodiester bond, okay? Here, so the phosphodiester bonds keep the nucleotide together, not only in DNA, but also in RNA and in oligonucleotides. I want you to know now that all this process is reversible. So in the case of dinucleotide formation in DNA, if the incorrect, let's pretend that this nucleotide was incorrectly added to the growing chain, the DNA polymerase is going to come in and remove it so that the correct nucleotide can be incorporated in the growing chain. And in that case, the pyrophosphate will be reunited and the whole process will happen in reverse. I hope you enjoyed this explanation of examining the mechanism of formation of dinucleotide, and that you have learned that the process is reversible.